Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use an impulse momentum diagram to write impulse momentum equations. Right? So what we're looking at here, we've got this object which is traveling at 5 meters per second at a 50-degree angle clockwise from the positive x-axis. We're going to imagine that it's then acted upon by the following forces: this 20 Newton force acting at a 60-degree angle and this 10 Newton force acting up. We're going to imagine that these forces act over a time frame of 2 seconds. Now, first let's talk about the impulse momentum diagram. You start by drawing a picture with the initial momentum of the system, which I have. And again, basically you start with a velocity vector, tack a mass on, now you've got the momentum vector. All right, second, you draw a free body diagram of the object. Now in theory here, in this made up example, the intention was that these are the only two forces acting on this. Now that's not an impulse diagram. This is just a standard force vector free body diagram. You turn those into impulses by multiplying them times time. Now these are impulses. Then you draw the final momentum vector for the system. Now, a lot of times you're not going to know a direction here, right? So you may have to kind of guess on that, which is perfectly fine. When you're dealing with vector quantities, it's quite common to not know a direction. You take a stab at it, and then you, if your directions are good, you'll get positive numbers when you solve it. If your directions are not good, typically a minus sign will show up. So I've assumed a velocity vector down and right based on the picture. Now, I say assume that. I have not gone through and calculated any values here. I just kind of use gut instinct here. Well, we're starting down and left. These are the two impulses. I think we're still going to end up down and left at some sort of unknown angle. But again, maybe we'll end up slightly up and right, or maybe we'll end up down and left or something like that. So again, the directions over here are somewhat guessed. All right, now let's talk about writing equations. So momentum, right, is a vector quantity. mv initial, or I guess I called it a 1 here, so I'm going to say mv1 plus integral f dt has to equal mv2. And again, this is a vector law. That means you can apply it by direction. So I'm going to go ahead and apply it in the x direction with right positive first. So when I look at my initial momentum vector, we're going to have mv1 cosine 50. And that's positive because that vector component points to the right. Now I'm going to look over here now. Impulse. This does not have an x component. This one does. The hypotenuse is going to be, and if you don't mind, I'm going to go ahead and write that, 40 Newton seconds, coming from the 20 times 2, times the cosine of 60 degrees, to give me the x component. And notice in the picture that that component points left, and I'm calling right positive, so we're going to have minus. Right? Right hand side equals, all right, the hypotenuse of this vector is mv2, and I want just the x component, so I'm going to multiply that by cosine theta. And again, where the theta is unknown, we don't know what that is right now. Now, keep in mind here that when we talk components, like if I were to draw these vector components, they're right and down. And this is what we could call v2x. Its magnitude is equal to, mv2x. So this thing would equal mv2 cosine theta. Now, in our equation, whether we put mv2x or mv2 cosine theta, it kind of depends on the problem. You know, sometimes one is more convenient than the other. I'll come back to that. For now, I'm going to put mv2 cosine theta. All right. Now we're going to do impulse momentum equation in the y direction. I'm going to go ahead and call up positive. You're perfectly free to call down positive if you wish. So you look at our initial momentum vector. Magnitude is mv1 multiplied by sine of 50 degrees is going to give me the y component. Now that y component points down, so I'm going to put a minus sign there. Now we're going to take a look at our impulses. We're going to have a positive 20 Newton seconds For this, no sines or cosines required because it points straight up. The y component of this vector, let's see, the hypotenuse is 40 Newton seconds. Coming from the product of these two, I'm going to multiply that by cosine 60 to give the y component. And you notice that the y component is down, so minus sign. All right, equals. Now looking over here, the y component of this momentum vector is here, equal to mv2 sine theta. So I'm going to go ahead and put mv2 sine theta. Keeping in mind that v2 sine theta, or mv2 sine theta, we could call, well, the v2 sine theta we could call v2y. That's what that is. Now, which I'm going to put this for now, but then I'm going to kind of glance my equations over and see which one I want to use here as I go to solve this. All right. So we got a pair of momentum equations here, and again, we get a pair because momentum is a vector concept. That means you can apply it by direction. You know, really what impulse momentum equations are, they're Newton's second law equations just kind of turned on their side. You know, basically, if you solve this equation here for force, you're going to get force equals mass times acceleration. Anyway, all right, let's talk about solving this thing. So if we go ahead and put numbers 10, 5 cosine 50 minus 40 cosine 60 equals 10 times 10 times v2 cosine theta. We have two unknowns in this. We also would have two unknowns here, and it's pretty easy. It's two equations, two unknowns to solve it. If you divide one equation by the other, you'll notice the v2's cancel. You can find theta, no problem at all. I think for this video here, what I'm going to do is this: I'm going to kind of think of this here as v2x, because now this equation has only one unknown. I'm going to go ahead and leave it as an exercise to the observer here. I solved this and I got minus 0.5 meter per second out of that for v2x. If we put numerical values here, again, this would be a 10, 5 meter per second, sine 50 plus 20 Newton seconds minus 40 cosine 60 equals, and again, this is 10 kilograms. And if I just call this v2y and solve this for v2y, I get positive 5.29 meter per second out of it. My solution came out positive. So let's talk meaning here. All right. The plus and minus signs aren't directly about left, right, up, down. They're about whether your assumed directions are correct. In my original picture, I've got v2x pointing to the right. I ended up with a negative number out of it. What that means is v2x in reality points left. Not because the minus sign means left. The minus sign in this case means opposite the direction shown in your picture, or the direction used to write the equation. All right, the v2y, you notice it comes out positive. All right, that doesn't mean it's up. It means that the assumed direction that you used to write your equation is correct. So the v2, the final velocity of this particle, let's see if I can pull up another one here. Good. The final velocity of this particle is 0.5 meter per second left. .29 meter per second down. I'm not going to quite get this to scale because I didn't have the room. So the net velocity vector is looking something like this. Now, again, this is meant to be kind of a beginning video here. I don't think the details are super important. I'll let the reader or whoever's watching the video do the rest of this, but you can get the net velocity now, the magnitude of that, by Pythagorean theorem. The magnitude of v2 squared is going to equal 0.5 meter per second squared plus 5.29 meter per second squared. This angle theta can be found, well, once you have all three of these, you can use any trig function you want, but the gold standard is to use the tangent function. The tangent of the angle theta is going to equal 5.29 over 0.5. So this theta is going to be the inverse tangent of this ratio. When I find angles, don't worry about this being left and down and using minus signs. I've got a right angle. I know that I'm going to get some number here between 0 and 90. That will be the angle between the negative x-axis and V2. So again, the intention of this video is to show how to write impulse momentum equations. You start by drawing the initial momentum vector of the system. You draw the impulse diagram. Basically, this is just a free body, tack on the delta t's. If the forces are constant, that's all you need to do is just tack on delta t's. If they're not constant, these need to be written in integral form. Draw your your final momentum vector. You will sometimes have to, oops, I forgot a vector symbol on that. You will sometimes have to guess directions. It's perfectly fine to guess directions, and what will happen is, just like right here, a minus sign will show up if a direction actually is not right. And again, you haven't done anything wrong, because in the end, by the time you work it out, I know the velocity vector now, including the correct directions, right? You write your momentum equations by equating the x component of this plus the x component of this. And again, when I say plus, I mean the vector sum. Like for example, this guy's x component points left, so it'd actually be minus, to the final momentum x component, right? Then you do the same thing for the y components. You start with the y component of this, the initial momentum, plus the y component of your impulses, equals the final y component of your momentum. And typically you can write 2, even up to 3 equations in a 3-dimensional problem. 3 would be it though. Momentum is a vector concept, and there's 3 independent directions conceivably we can write equations for it. So hope this video helps with these concepts. Have a great day.